This is 5.1 exponential functions. This is part 2. So make sure you go back and watch part 1. Part 2 is still dealing with exponential functions, but it goes into a slightly different application. And earlier in 5.1, part 1, we were just graphing exponential functions, talking about the growth and decay functions. Now let's talk about this thing called the natural base, the letter E. Well, kind of like the letter pi has a value, the letter E has a value, a decimal value that just keeps going on forever, 2.71828, blah, blah, blah. All right, so I'm going to ask you to evaluate certain things using that E. And the E function, if you notice on your calculator, look at the number 4, and then to the left of number 4 is this button called ln, but above that in blue is e to the x power. So you're going to be using the blue button, so e to the second power. So basically it's taking this number and it's raising it to the second power. That's really what it's doing, okay? So you're going to get a value of 7 point. And again, we're going to round it to 2 decimal places, 3 decimal places, whatever the instructions say. Let's say 3 decimal places. So 3, 8, 9. And then e to the negative first. So again, you would just plug that one in. E to the negative first. Evaluate that. E to the 0.25. Evaluate that. So you would get those decimals and round it to the appropriate directions. 3 decimal places, 2 decimal places, whatever the directions say. All right, so let's talk about what is graphing of this. Okay, so again, if you think about evaluating, you're just doing e to the 0 power, which is 1, by the way. Anything to the 0 power is 1. E to the first, well, we already know it's 2.7, blah blah blah, 2.7. All right, squared, e to the third. I mean, we're just plugging in numbers. -1, -2, -3, and we're just evaluating those again. But the calculator does it for us so much easier. So let me clear all these values out I made up from the last video. All right, so here I have y equals e to the x power. And again, if you look at the table, you know, e to the 0 power is 1, and e to the first is 2.7. So we already know that. E to the second is 7.38. E to the third is 20.1. Again, that's too high for us to graph for most of our graphs that we're ever going to do. But -1 is 0.36. -2 is 0.1. And notice that because I know E, remember E is 2.7 blah, 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 and it's to the x power. So remember, anything bigger than 1 is a growth function. So it's going to start off small, and it's going to get bigger. So e to the x power is going to look just like that. So 0, 1, 1, 2.7, 2 is 7.38, -1 is 0.36, and again, it's going to get really, really tiny and get bigger and bigger, 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 and it's an exponential growth. It grows. It never hits that line right here. So it never hits the asymptote y equals. And again, if I wanted to, I could put plus 2 minus 3. And so then it would raise it 2 spots. Or not raise. This is to the left 2 spots, left 2, and this is down 3. So we just talked about the transformations that we did in the last section, the first part of this video, 5.1, the very first part. So we just talked about transformations. So we could just take that same function, and it is growing, but it's going down 3 spaces. It's going left 2 spaces. So every single point is being shifted left 2, down 3. So even this, like this point right here, if we go left 2, down 3. So that point got shifted down there. And then we could shift every single one of those points and look at the graph. That's how it's being transformed. And I could put a negative out here. I could whatever I wanted to do to it, we could transform it to be able to make it look different. But that's the parent function, e to the x power. Now, where do you use exponential growth? Well, the most common exponential growth is with interest. Banks and mortgages and credit cards, anything dealing with interest is compounded interest. Now, back in like middle school, you learn things about simple interest. I equals PRT. That's simple interest. Simple interest is basically it will use, you just do the calculation one time, like a mortgage. A mortgage is simple interest, just divided up in between the 30 years or 20-year mortgage that you did. So, but a compound interest, it's the money that you earn that year or month or whatever how often you're earning it is being put back into the account, and you're earning it off of that new amount. So that's why it's called compound interest. So you have two formulas here that you need to be quite aware of. You're going to use these formulas quite often with this chapter. So compounding every single year. Now this P, you need to understand what the variables mean. The P is the principal, the amount that you start with. So if I had $10,000 and I put it into a bank account, the P would be the original amount, $10,000. So this is the principal amount, just like I equals PRT, that's the principal amount. The R has to be, this is your rate, and it has to be as decimal. Now, the T is obviously, that's time, okay? That's an obvious. Now, the N is something you need to pay attention to. The N is how often it's being calculated, how often calculation is being done. So, and we'll talk about that in just a minute, because banks could just do it yearly, they could do it monthly, they could do it weekly, they could do it daily. I mean, how often it's being calculated, that's what that N stands for. Now, and then there's a thing called continuous compound. This is the best case scenario if a bank gives you continuous compound. Like, it's faster than every second. I mean, as fast as a computer can calculate it, which is faster than a second. So it does it, it does it literally every continuous millisecond or something. It's calculating it. You're going to use this formula if it's continuous. So again, the principal times E raised to the RT power. So let's look at an example. So if George invested $8,000 into a bank account, and that certain bank was offering 4% interest, and George kept it in for 6 years. Now, what is the final amount that George would withdraw? So let's imagine there's a bunch of different banks. So Bank A says, hey, we'll calculate it yearly. We'll just calculate it one time a year. And so George puts $6,000 into this account at Bank A. And so we're going to follow that formula. You remember the formula is A. This book uses P. So P1 plus R over N to the NT power. Okay, so $6,000, 1 plus the interest is 0.04. Remember, this has to be entered as a decimal. Divided by N. Now, N is yearly. It's only being calculated one time. And then it's to the NT power, so 1 times 6. And then we're going to come over to the calculator and simply plug that in. So we have $6,000. This is where the calculator is going to come in extremely helpful on this. So 0.04 divided by 1. We don't really need to divide by 1. And we're going to raise that to the 6th power. So after 6 years, George would withdraw $7,591. If he just kept that money in there and for 6 years, came back 6 years later, and the banker said, let me calculate your money. He only has to calculate it one time. And that's how much he would have after 6 years. All right, well, it's good to all of us make mistakes. And on this video, I made a mistake. So it says $8,000. It's right there. For some reason, I wrote $6,000, probably because I saw 6 years. But anyway, it's a good thing we double checked. So that's $8,000. And notice the amount that George, something looked familiar, something looked odd to me, because if he started with $8,000, he's going to have more than $8,000. And the calculator came up with 7,500. I'm like, wait a minute, something's wrong. So I paused the video, read the problem again, and noticed my simple mistake. So it's okay. It's a good thing to double check. So $10,122.55. The other thing I do want to point out, notice I'm rounding to 2 decimal places, because with money we round to the nearest penny. All right, so that's $10,122.55. Now, semi-annual, we're going to do the exact same problem. Semi-annual is twice a year, so this is the n here is 1, here the n is 2. So it's going to look like 0.04 divided by 2, and then 2 times 6. And then we're going to calculate that. And then this one's going to be $8,000, 1 plus 0.04. Now, quarterly means 4 times a year, so it's being done 4 times a year. This one's going to be $8,000. Monthly is 12 times a year. Weekly is 52 times a year. Daily is 365 times a year. And continuous, I want to make sure P equals R, you're going to use PE to the RT power. So it's 8,000 times E raised to the 0.04 times 6. You're going to use a different formula when it comes to continuous. All right. So again, with monthly, you're going to use 12 times 6. And let me just jump ahead. So all of these basically look the same. The only thing I'm changing, notice this is 2, 2, because semi-annual is 2. This is 4, 4, because quarterly n equals 4. This is 12, 12, because monthly is 12. 52, 52. It's weekly. There's 52 weeks in a year. 365, 365, because there's 365 days in a year. And then notice this one, continuous. It's being done every second, faster than a second. I mean, it's continuous means continuous. It's being calculated. As fast as that computer can calculate it, that's how fast it's doing. Now, the more often it's being calculated, so I want you to notice the dollar amounts. This is, if George put the money in Bank A, he would have $10,122. If he put the same amount of money in Bank B, he would have $10,145. Notice this is more money. Bank B is more money because it's being calculated more often. And then notice Bank C is being quarterly. Notice it's more money. And Bank D, it's more money. The more often it's being calculated, the more money it's going to be made. Now, some of you guys say, well, it doesn't look like it's that much more. Matter of fact, if you look at daily and you look at continuous, it literally is only 13 cents more. Well, keep in mind a couple things. First of all, it's only $8,000. Now, $8,000 is a lot of money, but to some people, we could be talking about $800,000, or $8 million. It could also be a higher interest rate. It could be 5% or 10%. And it can also be, if the years was, 20 years, obviously the longer years that you put it in and keep it in, the higher the percentage rate. All of this affects it tremendously. So, it may not look like it's that much a difference, just a couple pennies. But again, the interest rate, the amount of money that you're investing, the time that you're doing, all makes a difference as well. So that's how you do compound interest and continuous interest. And again, these are exponential functions because they are exponentially financially growing. And this can be used in mortgages, credit card payments, and a savings account, specifically a savings account. You put your money into a savings account, you're talking about Bank A, Bank B, Bank C. That's why you should call around and look at the banks. That, some banks offer it, compounded weekly or daily. So depending on what your bank offers, I would put it in the more often Bank C than Bank A. I would probably do Bank C. So it does make a difference how often it's being calculated as well.